In this lesson we're going to look at the contact process for the manufacture of sulfuric acid. Now this involves a number of steps, and the first step is the production of sulfur dioxide. Okay, so we have to obtain sulfur dioxide, and this could be done in a number of ways. For example, we could simply burn sulfur directly in oxygen. Okay, so you've got sulfur plus oxygen to give you sulfur dioxide. Or it might involve heating or roasting metal ores that are rich in sulfur in the presence of oxygen. For example, heating or roasting zinc blende in the presence of air or oxygen. Okay, so here's a sample of zinc blende, and zinc blende is made from zinc sulfide, and by heating the zinc sulfide in oxygen we obtain zinc oxide and sulfur dioxide gas. And so it's the sulfur dioxide gas that we want for the contact process. Okay, the next step in the process is going to involve oxidizing sulfur dioxide into sulfur trioxide. You remember that if you take sulfur dioxide and add it to water, you'll get a weak acid called sulfurous acid. Now what we're after in this process is not sulfurous acid but sulfuric acid, which is a much stronger acid. Okay, so the next step is oxidizing sulfur dioxide, and this process is slightly more complicated because we're dealing with what we call a reversible reaction. So we've got sulfur dioxide plus oxygen is going to form sulfur trioxide. Okay, so let's just balance the equation. So we have 2 sulfur dioxide there and 2 sulfur trioxide here. Okay, so what we need to do is understand the conditions in this reversible reaction that favour the production of sulfur trioxide. And we're going to look at 3 important conditions for this. Now I'll be talking about reversible reactions and Le Chatelier's principle in a tutorial dedicated directly to reversible reactions and their mechanisms. At the moment we're going to consider how we can maximize the yield of sulfur trioxide. So the first thing we can look at is the pressure at which this reaction takes place. Now you'll notice that on the left hand side here of the equation we've got 3 volumes of gas, whereas on the right hand side we've got only 2. So because there are fewer moles of gas on this side, then by increasing the pressure we will favour the forward reaction. That's to say, we'll favour the direction of the reaction that reduces the volume. Okay, so you might think, well, let's just up the pressure in this reaction and get it as high as possible. Well, actually that's not what happens in this particular case, because even when the pressure is increased by just a little bit, between 1 to 2 atmospheres, the yield of the sulfur trioxide is very good indeed, over 99%. So it doesn't pay economically to increase the pressure of the reaction much more than this just to improve upon that 99% yield. Okay, so we have an increase in pressure, but the pressure doesn't need to be too high, between 1 to 2 atmospheres. So the next thing we'll think about is temperature, and before we do that we remember that this reaction is an exothermic reaction. That means that it's giving out heat. So if you increase the temperature of this reaction, it will tend to go in the back direction. So you might think that what we want to do in order to favour the forward reaction is to reduce the temperature. However, reducing the temperature will slow down the reaction rate. So you don't want to reduce the temperature by too much, because the reaction will never get going. So it's important to have a moderate temperature. So typically the temperatures for this reaction would be about 450 degrees Celsius. Okay, so we've got a fairly moderate temperature which isn't really favouring the forward reaction, but it is helping the rate of reaction because the particles are moving faster and they collide with each other and the reaction gets going faster if you have higher temperatures. Now, if we really want to help the reaction rate, as in most reversible reactions, we need to use a catalyst. Catalysts neither favour the forward reaction or the backward reaction, they just simply help to speed up the rate of reaction by making it more probable for particles to collide with each other. Okay, so in the case of this process, the catalyst that is used is vanadium 5 oxide, which will have a formula V2O5. Okay, so just to summarize this, to favor the yield of sulfur trioxide in this reaction, we're going to increase the pressure, but not by too much. Okay, typically around about 2 atmospheres, no more than that, because even at this relatively low pressure we're going to get quite a high yield of sulfur trioxide. The temperature is going to be moderate, around about 450 degrees Celsius. That actually goes against the forward reaction because it's an exothermic reaction. However, it helps speed up the reaction rate, which is also very important in getting this reaction to go. So we have a moderate temperature there, 450 degrees Celsius, and the reaction is assisted by a catalyst called vanadium oxide, which will also speed up the rate of reaction. So once we've got our sulfur trioxide, the next thing we're going to do is dissolve the sulfur trioxide in concentrated sulfuric acid. You might think, well, why don't we just add the sulfur trioxide directly to water, like this? That will produce sulfuric acid. However, because this reaction is so exothermic, it produces so much heat, that what would happen is that the sulfuric acid would just vaporize, which would be very dangerous. So we can't directly add the sulfur trioxide to water. Instead, it's added to concentrated sulfuric acid to produce a substance called oleum. That's H2S2O7, which is also known as fuming sulfuric acid. And then after the oleum has been obtained, it can then be diluted safely by adding water to obtain sulfuric acid, which is what we're after.